Thank you, everyone. So my name is Khurram, and I'm a PhD student with Rich, training, and we will evaluate the performance on the test set. And the question is, how is the test set going to look like for the training set? So before I show you the test set, I need to first explain the details of the experiment. So I'm going to do an experiment on the MNIST classification benchmark, and we're going to train a multi-layer feed-forward network with varying number of parameters. So the network has some input nodes, it has some features, and it has some predictions. And these predictions are basically the class probabilities in case of MNIST. Now, each feature in this experiment is going to have 50 incoming connections. And what that means is, this is what I mean by incoming connections. And these connections can be connected to any of the features in the preceding layers or be connected directly to input. So you can have skip connections, basically. And then each prediction unit is going to be connected to all the features. So it's going to look something like this. And the weights, so we're going to initialize all the weights to be in this range. The prediction weights are going to be 0. And then we're going to train until they hit a certain threshold. And this threshold value can differ for different experiments. So let's go back to our graph. We have this graph. And now we can see that the training set error looks like a flat line. That's because our threshold is 0.1. What about the test error? Well, this is what it looks like. So there is clearly a very strong trend that as your network size gets larger, your test performance improves. More importantly, when your network is very small, the test performance is very bad. The error is twice as much as when the network is large. So it seems like this hypothesis is correct, that in the supervised learning setting, when you have more parameters, you generalize better. Now, when I first read papers on this phenomena, most of the people seem to think that this is a property of deep neural networks. Something magical happens when you have deep neural networks. Also, by the way, these results hold for different activation function, initialization, stopping threshold, hyperparameter optimizer. So it's not just a cherry-pick example. So is it true that this is only true for multi-layer neural network? Well, we can test that. We can simplify our experimental setup, and the goal is going to be we're going to keep simplifying it until this phenomena disappears. Okay, so let's, instead of having a deep multi-layer neural network, we can have a single-layer neural network. So all the features are now in the same layer. Each feature is now connected to the input unit. So there are no hierarchical features. And all the other aspects of the experiments are going to stay the same. OK, what happens now? Well, same thing. So it doesn't seem like this is the property of deep neural networks. It seems like it's true for one single hidden layer neural network. So maybe this is the property of neural networks in general, or nonlinear learning in general. Well, we can simplify the experiment even more. Let's fix all the incoming weights of the features after initialization. So what I mean by that is, this is our networks. All the weights that are going from the inputs to the features, we're going to initialize them, and then we're going to fix them. And then we're going to never change them throughout the lifetime of the learner. And these prediction weights, these are the only weights we're going to change. And this is very close to a linear learner. It's not a linear learner because we have some softmax to get the prediction probabilities, but it's much simpler now. And the other thing I'm going to change is I'm going to change how the weights are initialized, specifically the distribution from which the weights are sampled. And this is because if the weights are too small, then you stay within the linear region of sigmoid, and we don't want that. We want interesting features. But the results I'm going to show are not too picky to this choice. You can have different choices, and you'll have the same results. And you can argue at this point that this is no longer a neural network. This is really like fixed random features, and then you're learning from those fixed random features. So are we going to see the same thing? So let's go back to our results. And seems like yes. So you don't need neural networks to see this phenomena. So this phenomena is not a property of neural network at all. Now, one difference here is that the threshold for this experiment is much higher. It's 0.30. And that's because for this fixed feature neural network, it's much harder to get to a lower error. But this also shows that the value you pick for the threshold is not that important. OK, so can we try to understand this? So let's start with a hypothesis I had at this point, that what could be happening. So I'm going to share the hypothesis first, not going to provide any evidence for it yet. And then I'm going to share a prediction I made with the hypothesis that if my hypothesis is correct, then this is what we should expect in our experiments, and then we'll test the result of that prediction. So my working hypothesis is that they're doing better because you're doing essentially a bigger feature search, and then stochastic gradient descent plays nicely with it. So more concretely, we can all agree it's a very reasonable claim that different features generalize differently. I'm not saying they generalize well or poorly, just differently. So imagine two features. Imagine there's a feature that is on when 90% of when you see a 1, 90% of the time that feature is on. Every other case, that feature is off. So feature is only 1 when you see a 1 with 90% probability. Imagine another feature that is on 10% of the time when you see a 1, and it's off in every other case. Now, in this context, I'm going to say that first feature is more general than the second because it allows you to make accurate prediction on many more examples. So it's more general in terms of it generalizes well on your training data set. And so when you initialize your features, you can expect that different features are going to generalize differently in this sense. And when you have larger networks, you're starting with more features. You're doing a bigger search in the feature space. Now, if you have more features, then there would be more features that generalize well. There would also be more features that generalize poorly. So I'm not saying making the network larger gives you anything magical. It's just a bigger search. More features that are good, more features that are bad. But then the second component comes in, which is that we're going to learn them by stochastic gradient descent. And if I learn them for a certain number of time steps, let's say I'm going to go over the data set 10 times. Think about our two features in the beginning, one that was on for 90% of the examples, one that was on for 10% of the examples. We're going to reinforce the first feature many more times because it'll be on more times, and every time the gradient will tell you to move in the same direction. So features that generalize well, when you train them with SGD, one sample at a time, they'll be reinforced more often, and they will end up dominating. So when you start with more features, some of them are good. In fact, you have more good features now. Those good features will dominate. So you would have found features that are more general on your training set. But because your test set is sampled from the same distribution, you can expect the same features to also generalize on your test set. So that's the hypothesis. But you can make a prediction based on this hypothesis, which is, well, if this is true, then networks that require fewer updates for learning on the training set to get to a certain threshold would generalize better on the test set because they have features that are more general. They'll be reinforced more often. So maybe you only have to go over the data set twice to get to a certain level of performance, whereas you would have to go over the data set many, many times if you're relying on more, less general features. Okay. So let's go back to our data from the old experiments and plot this, make a new plot. In this new plot, the y-axis is the same, it's the error. But on the x-axis, now I have number of weight updates it took to get to that threshold. And I'm throwing away the information about the model parameter. So we're going to take all the models that we trained. So we trained models starting from 5,000 parameters to 50,000 parameters. We're going to train all of them, and take all of them, and we're going to plot all of them on this single graph sorted by the number of weight updates it took to get to that error. So training set, again, is one line. That's the stopping threshold. Would we see a clear trend here? The answer is yes. We see a very, very clear trend that the faster a model learned, the better it generalized. And there's a very strong relationship between as you need more updates to learn, you generalize poorly. Now, there is a problem with this experiment, though. The main problem is that, well, maybe larger models both learn faster and generalize better. There's some other thing that's happening. We don't understand what it is, but when they are larger, that other thing makes them learn quickly and makes them generalize better. So we would like to remove this confounding factor of different sizes. And it's possible that all the large models are on the left end of this graph and all the small models on the right end of the graph. So let's do a different experiment. Now let's take 10,000 models of the same size. So now all the models have 10,000 parameters. They have been initialized with different seeds, so there is some stochasticity in them, and they would have different features. Now this stochasticity alone some of them would have better features, some of them would have worse features. So now we can remove this confounding factor of the sizes, and we can ask, would we see the same trend? The answer is yes. So 10,000 models trained with the same exact set of hyperparameters, just different initializations. If you sort them by how number of steps it took to learn to get to a certain error threshold, that is predictive of the test set performance. Okay, so that's some more evidence that is consistent with the hypothesis. Now, that's still not good if we can't use it to make new algorithms. The end goal is to come up with algorithms that don't have to use larger models, but they can still generalize well. So can we achieve that from this? OK, so I'm going to share an experiment. This is, there are many experiments I did which support this, but I'm going to share arguably the simplest one because of the time limit. So let's look at this new experiment. Now, it's a bit complex, so I'm going to take my time to explain it. What we're going to do is we're going to train 20,000 models, and each model has one feature. And we're going to train them for, let's say, 300,000 steps. And then I'm going to rank all those models based on their training error performance. So we're never going to test set is not used anywhere in the process. Now, features that generalize better in these 20,000 models would learn faster and would have a smaller training error. Features that generalize poorly would learn slowly, and they would have higher training error. Now, what we can do is we can take the 100 best features from those. Right? So we're going to take the features that learn the fastest, the 100 of them, and then make a new model that has those 100 features. OK. And then we're going to train this new model, and then we're going to compare it to a model with 100 random features. So what we would predict is that because these 100 features learn faster, they're more general, when we combine them and we get to a certain threshold, the model would generalize better if our hypothesis is correct. Now, this is not a perfect experiment because we don't really know how these features interplay with each other. So it's possible, for example, that the 100 most general feature all are listening to the same thing because that allows you to minimize the error the most, and then they're just very correlated. I have done other experiments that take care of that, but they were very computationally expensive and a bit too complex to explain. So, but let's just look at this one for simplicity. So this is the result. So on the training set, again, we trained both models to get to the same performance. And on the test set, we see that model that was trained with the 100 general feature has almost half of the test error than the model that was not trained like this. So it seems like this hypothesis lets us design new algorithms that can allow us to generalize, improve our generalization performance. And at no point in this process, we had to train a larger model. We did have to do a lot of computation, but the computation was amortized over time. So I'm not saying we're saving computation. I'm just saying that the understanding allows us that there are many ways to achieve this. One way is larger model. Other ways could be smarter algorithms. OK. So what are some conclusions? Well, it seems like the claim that larger neural networks generalize better on the test set is true in the sense that if you train them and you test them, you will see better performance. And the reason can be as simple as the larger search space and the larger search in the feature space, and then the SGD. And we don't necessarily need over-parameterized model to take an advantage of that. We can do this large search by coming up with algorithms that take small networks, but then do this search in other ways. So some ways of doing that is generate and test algorithms or other things that people have been exploring. And then we can achieve similar results. So that's it. Now, if you have questions, I would love to answer them.
Hello. How do you know how do you measure if a feature is learning faster?
So you learn for a fixed number of time steps. So let's say I'm going to train those 20,000 models with one feature for 300,000 time steps, so 5 epochs. And then I'm going to look at the training error. And if the feature minimizes the training error more, then it's helping with more of the examples, arguably.
So you're looking at each of them individually as like it's your only feature for that like training.
Yes.
Okay.
Yes.
And do you have a way of doing it if, like, say you have a giant neural network and you want to see which features in that neural network or even a linear model are the best ones? Do you
Yes.
have, okay. There's also
so I did an experiment, didn't include it here, where I start with a reasonably sized models, and then I train for a certain number of time steps. I don't train a feature for too long, and after I cut training short, keep the features that are most predictive, randomly reinitialize the other ones. And that also allows you to generalize better. And then there's a separate line of research, dynamic sparse training, and people have observed similar phenomena that a very similar algorithm like this with randomly searches over the feature space generalize is better. But they don't try to explain why. Right?
Thank you.
I have two questions here, front.
Yeah.
Okay.
Sorry.
So I have two questions. One is maybe an observation. So this hypothesis you made, it seems very similar to the lottery ticket hypothesis. So do you think there's some difference in your hypothesis or the results that you have seen compared to that? The other thing is, so you're doing feature selection in some sense, that you're using individual features.
Mm-hmm.
So it means that you have a pool of 20,000 features and you're selecting the best top 100 from those.
Yep.
So is there a relation between choosing them independently and using these independently selected features, and how do you make sure that these features combined would work better?
Yeah. So
like, is there any?
The two questions are sort of related, because the main difference between lottery, so this hypothesis is consistent with lottery ticket hypothesis, right? This is what you would expect on those experiments. But that hypothesis just says that this phenomenon exists and doesn't try to explain it at a granular level, right? So the one difference is that it's trying to explain it at a different level. And the second is that there is nothing that guarantees that when you combine the 100 features, then that's going to be good, because those features could be correlated. It just happened that in this experiment, on MNIST maybe that's not the case. But that's definitely not true in general. What you would like instead is a better algorithm would be you learn, let's say with one feature, then you add more features while that one feature is already doing its prediction. And then if you have a feature that's highly correlated, well, that's not going to be very useful, because that part of the prediction has already been taken care of. So now it really has to learn to predict something else to stand out. The reason I did this was because this was a bit simpler and easier to explain. That's the only reason.
You had an experiment where you showed that you can just have a broad network versus you can have a deep network and you can get similar trends. So do you think there is any role depth might have, or is it we can just design broad networks which also have a lot of computational advantages because you can parallelize broad networks more? So do you think we might be able to just design better algorithms by just doing scaling by the breadth?
So I think one clear benefit of depth is that it's sort of, you're reusing computation. So imagine that your feature is, two features are very similar, they have like 90% similar, and both are a function of the observation. You could probably make it a function of the other feature and save computation. So I see one clear advantage of having hierarchical features, where you can cache, like you can use computation basically. You don't have to do the same computation twice. But maybe there are other benefits too, I'm not sure.
Another thing to keep in mind is that deep networks here are not the usual feed-forward, fully connected that we are used to. They are like sparse in a sense, right? And the number of connections between those deep and the shallow ones were the same. So maybe you have to think a little bit more about that in context of your idea of fully connected.
Thanks. I thought the experiment was really interesting and very clear. I had a question about the last experiment you did with learning like one feature per model. So you said it doesn't necessarily lead to like learning with less computation as compared to learning like with the larger model. Do you think the wall clock time might end up being less because you're more able to parallelize the first kind of learning?
So I think the main takeaway message is I'm not sure if the wall clock time would be small. That would, I think, depend highly on the exact hardware you have. But the main takeaway point is that, okay, so imagine you have a hardware and the biggest model you can fit on it has, let's say, 100 trillion parameters, a very large model. Even in that setting, if you do a more continual search, if you do this search process over time, you can search over even larger models. So whatever compute you have, you can use that to achieve performance equivalent to larger models with that limited compute. That's really how I think about it. Yeah, so you're reducing the amount of computation you're using at one point, right? So you're amortizing computation over time.
Right. So if you just had like multiple GPUs and you couldn't fit a very large model on like one GPU, you could do the like smaller model thing across multiple GPUs.
That, but you could also do this process on one GPU by just taking more time.
Okay.
Whereas the larger model, you can't do that. Like if you have to make a prediction every time step, well, you can't. You have to make a prediction every time step. So it allows you to amortize, you know, this
Makes
search
sense.
over time.
Thanks.
Thanks. Regarding the confounding factor of training loss, the double descent works, at least some of them, refer to that peak as the interpolation point. And I don't exactly remember what that interpolation point means, but it implies to me that this is the point that after that you can reduce the training loss to 0. So at least if you're comparing the models after that point, then training loss is not a confounding factor, and you can like safely say that as you're increasing the number of parameters, it generalizes better.
So that's what I used to think too, that this point corresponds to when you can fit the training error perfectly. But I didn't really find really strong evidence for that.
Okay.
Seems to me like when I look at plot, it really is like they plot the training error, the functional parameter, and they see this thing. But like, can you not achieve 0 training error from this point? They don't do anything to show that clearly.
Also, like Belkin's group has some works about like this phenomenon in kernel regression as well. So if you want some simpler setting to understand it, you can look them up.
Yeah, that sounds great. Thanks.
Yeah, that was a great talk. Thanks for that. And just connected to the previous comments here, I was wondering if the point at which the double descent occurs, the shift, does that consistently occur when you normalize for the training in your figure? So because I did notice there's like an elbow.
Yeah, so when you fix the training error to a threshold, I don't see a double descent. So it could be the case that this double descent is due to the interplay of optimization and generalization. Something more complicated is happening. But yeah, in any of the experiments, I did not see the double descent, so-called double descent phenomenon.
Also, another question I had was if you tried making connections with linear regression and the different types of regularization they use.
No, so I didn't. I tried different activation functions, but I didn't try regularizations.
So the experiment you did, it makes a lot of sense. I was wondering if you could do the reverse to make the conclusion complete, like select the features that you know are bad, and still have a bigger network, but all of the features are now bad. In that case, would a bigger model do better, or I don't know?
Right. So I didn't do that experiment, but I did do another experiment where I took the 100 worst features and I trained using those. So I didn't increase the size of the model like in the last experiment, but I don't have that because that model never learned anything meaningful. It never got to the threshold, right? So those features are so bad that it just doesn't learn. Which kind of makes sense. If I'm connecting to 50 random features and I'm searching over 20,000 features, there are going to be some features that are just connected to the borders and they are just completely meaningless. So all of the like 100 worst features tend to be those features. They don't have information to make any predictions.
There is an online question. How do you compare your work to the knowledge distillation from a large network to a smaller network?
Yeah, so that's another interesting phenomena where it seems like, this is my intuition, I don't know if this is true or not, that if you start with small model and you learn using gradient descent and you're not doing a big search in the feature space, then you don't generalize well. But if you are trying to distill a model that generalizes well, then you're giving it a stronger signal in terms of optimization. You're literally saying, don't just fit this target, fit this exact thing, and then maybe then SGD can just discover the right features, right? But it doesn't seem like if you just use randomly initialized one and you learn them, it finds those general features.
Hey, so we didn't see the ski jump on any of your plots.
Yes.
My question is why? So all of your experiments were done with MNIST. Is this a function of MNIST? Is it more general?
It's not a function of MNIST because the double descent paper has results on MNIST. So the earlier graph I showed, basically the hand-drawn graph that's based on a graph from the paper, which is on MNIST and which does show double descent.
So do we know when it will occur and when it won't?
So
is there a data set property?
Yeah, my prediction is that it's because of this. So if you look at this training error, it's not the same at every point. It's different. So, there are these two things happening where you're optimizing better at a certain point, and then you're measuring the generalization performance. So I guess it's the interplay of those two. So I could do an experiment in which instead of training them to get to a certain threshold, I just train all of them for, let's say, 2 million steps, and then plot, and then I will see a similar training error curve. Then maybe I'll see the same test error set. But I haven't done that experiment.
I have a question. So I wonder, have you thought of, or are there any candidates for algorithms that identify features that can learn quickly beforehand, so you can selectively focus on the good features and learn on them and throw away bad features before you waste computation discovering that those features are bad?
So I have an algorithm, but it still uses computation. So what I was looking at a long time ago was, when you do this feature search, and let's say you're learning with these 100 random features with large step sizes, they're going to influence your prediction as well, right? So this search process can make your performance bad. And if you care about online learning, then you don't want that. So what I experimented was with the idea that you have these features, they are learning, but they're not influencing prediction. They are learning as if they're making the prediction, but they're not actually making the prediction. And that allows you to discover features that are consistently correlated with the error in the same direction without actually influencing the prediction. But you still use computation.
I think this is our last question, actually.
Hi, Khurram, thanks. So following up Joseph's question, so it seems quite weird that you don't see double descent, because you see the sharp hill there we have has already larger error compared to the first valley, right?
So yes, I definitely agree that something interesting is happening there, right? It's like seeing this plot, you can definitely say that, okay, larger models sort of do generalize better because it's not just optimization because of this weird thing that's happening in between, right? But
so let me complete my question.
Okay.
So you're doing for the sharp hill, you're doing more training, and you are your training error is small, and you are showing result that, okay, do less training for the sharp hill, and the error will become much smaller than the valley, right? So this is some sort of this is very weird. So, I mean, if you are cutting your training error, to make it flat,
mm-hmm.
it should favor the first part of your curves, the first part of your.
But I'm not just cutting; it's a bit of both. So this I'm not just training this second part less. I'm also training this first part much more. So this curve has basically been flattened. It's not like this is what I'm plotting, right? So
even worse. So you're favoring the first part of your green curve, and you are destroying the green curve as you go to the right. So I mean, the sharp hill you have in the middle should be even sharper. Should even go higher.
But I think so. I think we should ask a different question, which is, does this make sense in the first place? We have accepted the double descent, but when you saw it, did it make sense? You were like, whoa, that's sort of weird. So that's my intuition. And then the reason I did my experiments was because I was skeptical. I was like, well, I don't think this is happening. This seems weird.
Could you regenerate these results on the MNIST?
These ones?
Yes.
The double descent one?
Yep.
As in I can re-implement the paper.
Yes.
Yeah, so that would be a way of doing it. I could do that. I haven't done that. But I was skeptical of the claim, and then I saw my own results, and I'm a bit more confident in my skepticism.
Okay. Thank you.
Thank you, speaker.
Thank you. Yes.
So in that plot, like, where would you draw the threshold that you